Part 3 is not very long, and this is the final topic called no-pumping theorem, which is due to Rahav, Horowitz, and Jarczynski. So this is a result in 2008 from the group of Chris Jarczynski at Maryland. And I personally think this is very interesting, at least theoretically very interesting. So let me discuss this topic in detail. And I believe that this no-pumping theorem is interesting mainly in the context of small systems. But the theorem is valid for macroscopic systems. So if you can find any interesting application for macroscopic systems, that's nice. Please tell me about that. Okay, so but anyway, let me start discussing the motivation in the context of a Brownian particle confined in a potential in one dimension for simplicity. And I assume that this space has periodic boundary conditions, so it's a kind of ring. And the question is, can we generate a directed current of the particle, this Brownian particle, by modifying or controlling the potential in periodically in time? So you modify this potential according to certain protocol and try to get a directed current of this particle. So this may be relevant to transport phenomena in biological systems by using like molecular motors, or I don't know about this, but probably you want to design some nanoscale machines which carries very small particles artificially. But anyway, so this is a question. And actually, this question itself is not very interesting because the answer is obviously yes. Okay, so suppose we have this potential profile and you want to generate a directed current in this direction. Then what you want to do is first raise this potential barrier very much. So then this guy cannot hop to left. And then you lower this energy, the energy of this. And if you want, you can lower the barrier here too. Then this, with large probability, this hops here. Then after some time, you raise this potential barrier here, and then you repeat the same thing. And then with very good positive probability, you will get a directed current of this particle. So the answer is yes. But look, in this case, of course, we needed to change both the potential depth EJ and the barrier BJK. So what is this BJK? Well, let's go back to page 2 of the same part 3. So we started from this assumption of detail balance condition, and we argue that this condition implies that omega is always written in this way. Okay, so this part is symmetric in K and J, and this takes care of the energy. And this is in general very arbitrary, but one natural choice is that A is given by something like this. And here is the potential barrier between J and K. So that's this B. Anyway, so here, in order to realize this protocol, we had to control both the potential depth and the barrier height. So the question is, suppose that for some reason it was very hard to control this barrier, and you can rather easily control E. I don't know, but suppose that is the case. Then the question is, can you pump? Can you create a directed current only by modifying the potential depth EJ? And of course, the answer is no, because this is no pumping theorem. Okay, so here is a more careful formulation. And so we consider a Markov jump process with this transition rate. And again, so this is the form we have seen in page 2, okay, this form. And but this is a general, I said that this is a general form, but here I say that this A is time independent. So we do not control here. And we also assume that all states are connected by A. So A is irreducible, but actually this assumption is not important at all because we want to prove a no-go theorem. So if this is not the case, you just only consider the set of states which are connected by A and repeat the same argument. So this is not at all essential. And more important is that this A is time independent. And of course, it's symmetric in K and J. And we want to control EKT according to some fixed periodic protocol. Okay, and periodic means that it's a periodic function of time. Tau naught is some constant, and this is controlled in a periodic manner. Okay, And now then we start from some initial state and solve this master equation. PT is the solution. And then recall that we discussed the notion of probability current in part 2. So let's go back to part 2. This is part 2, page 32, as you see. And here we define the notion of the probability current. Okay, so here you are at J, and this is a rate that you go from J to K. Here you are at K, and this is a rate that you go from K to J, and you take the difference. So this defines the net flow of probability from J to K. Okay, and it satisfies this relation. And of course, the most important, we use this. It satisfies the continuity equation because the probability is conserved. Okay, so this is probability current. So this is a definition, but it's always confusing to use both R and omega. So let me write this in terms of omega. Okay, and you are at K, and this is from K to J. You're at J and J to K. Okay, so this is a main object of study here, and the theorem states that if you take the long time average of this J, so you integrate from 0 to T, this is not the temperature, some very big time, and you divide by T, and the T goes to infinity. Then the statement is that this is 0 for any K and J. So there can be no net probability, and the pumping is impossible. Okay. Here is one important remark. We started from the assumption of detail balance condition. Oops, detail balance condition. And detail balance condition in general means this. So in our case, this was the canonical distribution, but this is the more general formulation of detail balance condition. So this if omega satisfies this, we say that omega satisfies the detail balance condition with respect to this probability distribution PS. And okay, so this is a statement, and you do not sum over J and K. This says that this thing and this thing are equal. And of course, this implies that the corresponding probability current J is simply this minus this is from this relation 0. So yeah, flow from K to J is exactly equal to the flow from J to K. So this is 0. So this means that you don't have any probability current in a steady state in a dynamics which satisfies detail balance condition. But this is only for this stationary distribution. Okay, and of course, in our case, we use protocol to modify omega. So of course, the state is always sort of driven by this time-dependent protocol, and the state can be very, very far from equilibrium all the time. So this argument does not work at all. So of course, this can be non-zero. Okay, and you can easily pump a particle for a short time by precisely controlling this protocol. Okay, but the question here is, can we make a really steady current, or can we make a current which persists for a long time? And the answer is no. This is by no pumping theorem. But actually, this observation about detail balance dynamics is actually important. So this tells you that if you have a detail balance dynamics, you don't have any probability current. And the essence of proof is that to observe that by taking the long time limit, by taking the long time average, there appears some effective detail balance stochastic dynamics. And from this fact, you prove that there is no net current. Okay, so this is the precise statement of the no-go theorem, no pumping theorem. So let me discuss the proof. And actually, this proof is due to Christian Maas, Karen Netokny, and Thomas, which was published in 2010. And I think this is a very elegant proof of this very interesting theorem. So let me explain this. And the philosophy is, as I said, we construct some detail balance stochastic process that emerge from long time average. Okay, and the proof consists of 3 steps, and this is step 1. In this step, okay, so the basic assumption is that our omega is written like this, and this is time-dependent part, and this is time-independent symmetric part. In this step 1 of the proof, you do not see any EKJ. You do not see any time-dependent part. You only see A. That's very interesting part of this proof. And first of all, you sum over J. You sum over one of the index of AJK. Actually, AJK is symmetric in, so this is this can be written in either way. But anyway, you sum over one of these index, and J for all J which is not equal to K. Okay, and you call the result VK, and then you define TJK by this. So when J and K are not equal, you divide AJK by VK, and when J equal K, this is 0. Okay, and obviously this is non-negative, and actually, since I assume the reversibility connectivity, this is strictly positive, so you can divide by VK. And if you sum over J, you simply sum over here. But you get exactly the same thing, so you get 1. So you see that T is a stochastic matrix. Then here is a very essential, important lemma. First of all, T has an eigenvalue 1, but you know it's this is a stochastic matrix, so you know that it has an eigenvalue 1. And the more essential part of the lemma is here. And this eigenvalue 1 is non-degenerate. And actually, if you know the Perron-Frobenius theorem, we quoted in part 2, page 25, then this is an obvious, straightforward consequence of the Perron-Frobenius theorem. But we decided not to make use of the Perron-Frobenius theorem. So here is an indirect way of proving this lemma. You define R by this. Then you will find that this is an irreducible transition rate matrix. Then you can use the convergence theorem in part 2, page 34, this theorem, and this is for R, but anyway, you can use it and to prove this. Okay, believe me. And so we have this. Now we also know the corresponding eigenvector. Here we define this quantity and call it V, and so we can consider this vector V. And actually, this is the eigenvector with eigenvalue 1. Why? Well, and here is detail balance condition. Okay, consider this product, no summation, TJK times VK. But this is very simple because this was the definition. So it's AJK. And A is symmetric in K and J, so it's AKJ. So you do the same thing and you find this. Well, this is very trivial from this definition and the symmetry of A, but you see that this is a detail balance condition. This is a detail balance condition for a stochastic matrix T, okay? Because this is you are at V, and this is probability that you go from K to J, and this is the probability. Oh, this is not necessary probability, but anyway, this is a kind of detail balance condition. Okay, if V is a probability distribution, then this is precisely detail balance condition with respect to V. Okay. And anyway, this immediately implies this because you want to sum this over K, and you simply sum over K, so you get this. And here you simply sum over K, but you can just sum over here. And since this is stochastic matrix, you get 1, and you get this. And this says that this V is the corresponding eigenvector with eigenvalue 1. Good. This was step number 1. I go to step number 2. Here we look at the T-dependent part. Okay, and our transition rate is written like this. And actually, I cheated a little bit. I wrote AKJ before, but AKJ equal AJK. So this is our transition rate. From this, we look at the escape rate, which is defined, as you know, by summing over J, which is not equal to K. And now you use this. So here, this does not depend on J, so you can pull it out here, and you just sum over here, and you get V. So this lambda is written in this form. Very interesting. And now omega. Omega is like this, of course. And you multiply this by VK, and you divide by VK. And look, here you see this. So this part gives you the escape rate. And here, I think you remember, this is the definition of T. Okay, so here you get T. Very interestingly, this transition rate omega is written as a product of the escape rate, which is time dependent, controlled by our protocol, and this TJK, time independent stochastic matrix, which is defined solely from A. Good. So this is an important observation. And now this is the definition of the probability current. I plug in this relation here and just change the order like this. And now look here, here we have current, and here you have T. And here you have this product of lambda and P. Motivated by this very interesting expression, we define these long time averages. First of all, this is, of course, natural object to look at. This is just a long time average of the current. So we want to show that this is 0. Okay. And here, probably physically speaking, I don't know what does it mean, but physically speaking, a natural quantity you want to look at is the long time average of PKT. But this relation suggests that probably it's theoretically more interesting to look at the long time average of this product, lambda times P. So this is a bit confusing notation, but we call the long time average of lambda times P rho. Okay. And actually, you might ask that do these long time averages exist? And yes, actually, we assume that everything is periodic in time, and then you can use like Floquet theorem and to easily prove that these long time averages exist. And actually, this is the only place we use the assumption of periodicity. So if you want to prove the theorem with minimum assumption, then instead of assuming the periodicity of the protocol, you assume that these long time averages exist. But that's too abstract. So one condition that guarantees the existence is the periodicity. And also this periodicity is very well motivated by our physics motivation. Okay, and that was a remark. But anyway, so we had this very interesting relation. So we defined we introduced these long time averages. Then, of course, you want to take the long time average of this equality. So from here, you get this, course. And here you have, here you have T times this thing. So this is average, long time average, minus T times this thing. And so this, you get very, very suggestive form, very nice form for nu and T and rho. Okay. And we also recall from part 2 that this P and J probability current satisfy the continuity equation. Okay, and now I want to take the long time average of this equality here. And what is the long time average of P dot? Well, P dot P is a probability, so it's always in between 0 and 1. So if you integrate this thing, it can be at most 1, right? So you divide by T and take this limit. Of course, this is 0. This is 0. So the long time average of this continuity equation tells you that nu is divergence free, like this. So we got, we consider this very natural object. We consider this not very natural, but theoretically natural object. And then these two guys satisfies these two relations. Okay, so that was step number 2, and this is step number 3, and it's very short. Okay, now we have these two important relations, and now from this we want from these two, what you want to do is to sum this over J, which is not equal to K. And the left, so you first look at the left-hand side. And then since TJJ is 0, this is the same as summing over all J. And this is a stochastic matrix, you get 1. Here you get 1. And here you get this. And of course, this sums up to be 0 by this. So you get this. And since TJJ is 0, this is rewritten like this. So this means that this rho as a vector is is an eigenvector of T with eigenvalue 1. Then look at lemma 1 in page 18. Lemma says that T has eigenvalue 1. Of course, we know it, but it's non-degenerate. And we also know that V is the corresponding eigenvector. So this is the unique eigenvector with eigenvalue 1. So this means that rho is proportional to V. C is some constant. Okay, now we again go back to this relation again. So now we plug this in here. So this is written in this way. And I recall that this T and V satisfies this detail balance condition. So as I promised in the beginning, we use this effective stochastic process with satisfying detail balance condition to conclude that this is 0. This is vanishing. And of course, this is the long time average that we wanted to consider. So we have proved the no pumping theorem. Okay. I think this proof is also theoretically beautiful and suggestive. Okay, that's basically all, but I have one more slide. And so we have shown that you can never pump a Brownian particle, by only controlling the potential depth. But is it true? What about this example? So you have all these shallow minimum, and you have one deep minimum here. Okay, so this omega denotes the transition rate. So everything, all the transition rates are the same, but only this transition rate, escape from this deep minimum, is much smaller than the rest. Okay, so this is a very simple case, and what you want to do is here. So your particle wants to be here, right? And then you slowly change your potential and change it to this form. Now your particle wants to be here, and this is realized by only controlling EKT, right? You don't have to control the barrier. Barriers are always the same. And now your particle wants to be here. You modify potential like this, so you can pump. You can repeat this, and you can do it periodically in time, and you can pump. But we have proved the no pumping theorem. So is there anything wrong about the no pumping theorem? Of course not. The proof was completely rigorous and clear. So it means that there is something wrong about this argument. So why doesn't this pump work? So please think about this. Okay.